Okay, let's talk about linear DEs. Okay, so here's a theory. A DE is linear that term linear if it's linear in Y. We don't care what the X's are doing. We care if every function of Y is a linear function of Y and its derivatives. So if every version of Y or Y prime or Y double prime, if they're all linear functions of Y, you got yourself a linear DE. So this guy here, this is a linear DE. And you look and you say, well, there's a lot of nonlinear stuff, but that's all X's. All of my Y's are to the first power. I've got a Y, I've got a first derivative of Y and a second derivative of Y. I'm not taking any trig functions of Y. I'm not doing exponentials of Y, logs of Y. I'm not doing anything nonlinear to Y. This is a second order linear DE. This guy here, on the other hand, say we had Y prime squared plus 3x equals 7. That's a nonlinear DE because I've got some version of Y squared. Or if I had, I don't know, Y prime equals cosine of 3xy. Here I've got a Y inside a cosine. That's nonlinear. So these two would be no, those are not linear. This one is linear. Okay, we're going to learn how to solve not every, but quite a few first order linear DEs today. First order meaning we only have the first derivative, no second or third derivatives, linear DEs. Okay, so all of these can be written something like this. If you have a first order linear DE, you can write it out like this, where P of X and Q of X are only functions of X. And again, those might be nonlinear functions of X, but nothing nonlinear in Y. Then what we do is we find what's called the integrating factor. And our integrating factor, IF, is e raised to the antiderivative of P of X dx. So we take this guy here, that's a function of X, find his antiderivative, and make that thing, no matter how nasty it is, the exponent of E. Then we multiply through by that integrating factor. Multiply everything by that integrating factor, both sides. So you'll get Y prime times whatever that thing is, plus P of X times Y times that integrating factor equals Q of X. The integrating factor. The reason we do that is something special is going to happen on the left-hand side. The left-hand side then will always be a chain rule of Y times the integrating factor. The left-hand side will always equal the chain rule derivative of Y times that integrating factor. And that will make more sense once we do an example. So we're going to unchain rule this. We're going to squish this back together. Or I keep saying chain rule, it's product rule. The left-hand side will be the product rule of y times the integrating factor. So we'll unproduct rule this, rewrite it as a derivative, and then we integrate both sides. The question is whether or not we'll be able to integrate this side. That's the setup. That works every single time. Getting to here is always going to work. The question is, sometimes we'll get over here and we'll get something that we don't know the antiderivative of. So we're stuck. Remember, it's a lot easier to take derivatives than it is antiderivatives. There are plenty of functions out there that do not have a nice, pretty simple antiderivative. Okay, so let's start simple. Let's say we've got y prime plus 2y equals x. So let's identify our stuff here. Our p of x, the thing in front of y, regular old y, is just 2. And my q of x, this guy on the other side, is x. Then my integrating factor will be e raised to the antiderivative of 2 dx. So I take the antiderivative of this guy and make that a power of e. Antiderivative of 2 dx will be 2x. Now I know technically there's a plus c there, but we don't, never put your plus c in your integrating factor. So antiderivative of 2 dx is 2x. Our integrating factor is e to the 2x. So now we multiply everything through by that integrating factor. So look here, I multiplied everything by that. Now the whole point of this, what's cool about this, why this works, is the left-hand side is now the product rule of y times the integrating factor. The left-hand side is the derivative with respect to x of y times e to the 2x. Let's check that. Let's think product rule. Remember product rule, derivative of the first times second plus derivative of the second times first. Okay, so derivative of the first, leave the second alone. Plus, leave the second alone. Derivative of e to the 2x would be e to the 2x, and then we got to chain rule that, we pick up a 2. We're not doing anything with the right side. That just hangs out for a minute. We just want to verify at this moment that this thing, this left-hand side, is the product rule of y times the integrating factor. So let's write it like that. So now my dE becomes the derivative of y e to the 2x equals x e to the 2x. Now I integrate both sides with respect to x. So my next step, this is important. A lot of times mistakes happen here. I'm going to take or apply the integral dx to both sides. I'm not just going to write, I'm not going to do this. That's meaningless. That doesn't make any sense. You can't do that. You will never have this symbol without a differential here. So we're not just putting an integral symbol on both sides. We're putting an integral symbol and a dx on both sides. Okay, now on the left-hand side, I have, this is a chain rule in here. In a sense, these dx's cancel, and I have the antiderivative of the derivative. This is going to happen every single time. Every single time, the left-hand side, this is all going to cancel out, leaving just y times the integrating factor. I mean, this is a step you have to write out. That's part of showing your work. But every time you're going to get y times the integrating factor. Then the work is finding the antiderivative of the other side. So here we're going to have to do a little bit of work. See, this is already, that was a very simple looking DE. It wasn't even that nasty looking. And I'm going to have to do integration by parts just to do this antiderivative. So this is a very powerful method, but if this had been, say this had been an x squared, I'd have to do integration by parts twice. If this had been, oh, I'm trying to think of something that would be impossible to do. I can't think of anything off the top of my head, but there are plenty of things we could have had here that didn't even look that bad. And then we get down here and we go, oh, there's no way to take that antiderivative. There's no general solution to that. I do one of those, or I at least go through that in the first video. Okay, so now we have to do this nasty integration by parts. So I need a little space here. So I want to do the antiderivative. This is some side work, xe to the 2x dx. So I'm going to let u be x, du will be dx, v and dv. dv will be e to the 2x, v, we're taking the antiderivative, e to the 2x over 2. So this will be u times v minus antiderivative of v du. E to the 2x over 2 dx, which will be x e to the 2x over 2 minus, and then we'll pick up an extra 2 on the bottom, e to the 2x over 4 plus c. That's where we finally get our plus c. All right, so that's all here. That was our right side. Now we were trying to solve this for y. So our last step every single time is just divide through by this integrating factor. Just get that y by itself. We're already done in implicit form. If we just wanted an implicit solution, we're done. There it is. If we want an explicit solution, let's divide through by this guy. So this one's not going to be too bad. Those guys will just cancel out. It was important, though, to put the c in here. If you wait until the next step to put your plus c in, you're going to get it wrong. The c needs to go there when you take this. When you take this antiderivative. Okay, so remember multiplying, or let me say this, dividing by e to the 2x is the same as multiplying everything by e to the negative 2x. So I'll get y equals x over 2 minus 1/4 plus c e to the negative 2x. Or I could have written it c over e to the 2x. Either of those is fine. Okay, so it's a relatively simple process. Sometimes we get a nasty integral we got to do. Sometimes we get an integral that's impossible. Okay, let's do another one. Okay, let's do this guy. Y prime plus 2 over xy equals 0. So our q of x over here is 0. It's not going to be too bad. So my p of x, the guy in front of y is 2 over x. I'm going to need his antiderivative, dx. That would be twice the antiderivative of 1 over x. So that's twice the natural log of the absolute value of x. Remember, we don't need our plus c yet. Now, here's a hint. Anytime you have a question that looks like this and you got a number there, whether that's a 2, a 3, a 5, that number is the most important thing in the problem. That number is a lot more important than you think it is, because we're always going to bring that in as an exponent using rules of logs. So this would be natural log of x squared. Notice I dropped the absolute value because x squared is always positive. So my integrating factor is e raised to that, e raised to the natural log of x squared is just x squared. So if this had been a 3, I would have gotten x cubed. If that had been a 7, my integrating factor would be x to the 7th. And we'll do one like that in a minute just for fun. So this is what we multiply everybody by, both sides, x squared. 0 times x squared, of course, is still 0. So let's clean that up a little bit. Oh, that would be what? 2yx. Then, if we've done our work right, the left-hand side should be the derivative with respect to x of y times this guy, the integrating factor. So we're going to unproduct rule that and write it like this. Let's check and make sure we did it right. Lost my prime. Derivative of the first times the second plus derivative of the second, derivative of 2x, or derivative of x squared is 2x, times leave the first alone. It's right. Then we integrate both sides with respect to x. Don't forget your dx here on both sides. The left-hand side, there's nothing to do. Remember, the whole point of this is I'm taking the antiderivative of a derivative. Those are inverse mathematical operations. The right-hand side, the antiderivative of 0 is a constant c. So my solution is y equals c over x squared. And we could easily check that solution, go back to the original DE and check it and make sure it works. Okay, I guess we probably got time to do one more. Okay, I'm just gonna make one up. Let's say we've got y prime plus 3 over xy equals x to the 4th. And maybe, I don't know, for fun, we'll do an initial value problem. And let's say y of 1 equals 1. Okay, so we do our integrating factor is e raised to the antiderivative of 3 over x dx. That'll be e raised to the antiderivative of 3 natural log of the absolute value of x. Now we're going to take our positive branch here and assume the x is positive. We've done that a couple of times before. So this will be e raised to the natural log of x cubed. Here I just completely dropped that absolute value. Remember, we always end up with a family of solutions. I'm taking the family of solutions here. I made a choice and assumed x was positive. I only want my solutions on the right half of the plane, so I don't have to worry about that absolute value. That'll be x cubed. Multiply everything by that. Over here on this side, we'll get x to the 7th. Let's clean this guy up a little bit. And then we should check this, that this is in fact the derivative, the product rule of y times x cubed, derivative of the first times the second, plus there's the derivative of x cubed, leave the first alone. Space there. Then we take the antiderivative of both sides, dx. Don't forget that dx. If you don't write the dx, you lose points. This will be y x cubed equals, what is it, x to the 8 over 8 plus c. That's where the plus c comes in. Then divide everybody by x cubed. Y will be x to the 5th over 8 plus c over x cubed. Oh, you can't see it.